one final point here, and that's the following. What assumptions do we make on the noise? I mean, when we derived the probability of error expression, we assumed that the noise was Gaussian. Now, the question is this also Gaussian, these interference terms? They're not, really. They contain basically 4 possible values. So, because a Gaussian is a continuous random variable, these individual terms are not well approximated by Gaussian random variables. However, when you have a large number of interfering users, there's a theorem of statistics called the central limit theorem that takes over. So what will happen is each of these terms individually doesn't look Gaussian, but when you add up a lot of them together, they approach the Gaussian distribution. So in fact, as U becomes large, this is an approximation, but it's quite an accurate one. Excuse me, the variance is not an approximation. This is the exact variance. What's approximate is assuming that it's Gaussian to get back to all of our analysis from before. Okay, let's furthermore assume once again we'll use our notational shortcut. Call a sum from j equals 2 to u. I said this variance is for user 2 it was v12. In other words, the variance of the second user's interference with respect to the first user. So I can call this v1j plus n0 over 2ts. Furthermore, let's assume v1j is equal to v. They're all the same for all j. That's a pretty reasonable assumption. So therefore, the variance of the interference plus noise, let's go back to calling it sigma squared, is u minus 1 times v plus n0 over 2ts. So what does this mean when we throw it back into the probability of error expression? So let's follow our recipe from weeks and weeks ago. So first thing we need is noise-free filter output, match filter output. Noise-free match filter output in this case is, I'm using Sx now as my match filter. So Sx dot S1, excuse me, Sx dot alpha 1 S1, which is equal to alpha 1 times S1 is root NB times Sx. Alpha 1 root NB Sx dot Sx, which is root NB alpha 1, because this is 1. Second thing we need, actually I can't remember what order this goes in. We need the threshold, optimal threshold. Alpha 1 takes values plus 1 minus 1, so the optimal threshold is 0. And the third thing we need is noise variance. And that is equal to this. U minus 1, the number of users minus 1, times the interference variance with respect to each user, plus n0 over 2ts. Okay, now we throw it into the RFC expression. And we have probability of error NB alpha XCB. This is +1 and -1. So in the RFC expression, we see S0, so that would be +1 for here. So we have root NB divided by root 2 sigma squared, which is equal to 1/2 RFC root NB. Actually, let me back up. RFC of the noise-free filter output when the bit is 0. That's what the expression is. S0 or root 2 sigma squared, which is 1/2 RFC. The noise-free filter output when the bit is 0, that is +1, so this is NB, divided by root 2 times U minus 1 times V plus N0 over 2TS, which is equal to 1/2 RFC times the square root of NB divided by 2 U minus 1 times V plus N0 over TS. Okay, so a few observations at this point. I can manipulate this a little further. Actually, let's do that. And I'll multiply top and bottom by TS, and I get TS NB divided by 2TS U minus 1V plus N0. And remember, from long ago, we argued TS times NB is equal to the energy per bit. Basically, in the absence of interference, we have this, 1/2 RFC root EB over N0. In the presence of interference, we have this, EB over this interference variance term, plus N0. So a couple of remarks at this point. First, interference costs. So if let's see, what do we want here? We want probability of error to be as small as possible. So RFC is a decreasing function. In other words, as this argument gets larger and larger, it will decrease. Furthermore, if this argument gets smaller, it will increase. So where do the number of users come in? They come in here. It's in the denominator. So as the number of users increase, this ratio will decrease, and therefore probability of error will go up. Another thing to notice is that even if you had a fancy-dancy receiver cooled down to almost absolute 0 so that the noise vanished, you would still have an error floor. So even if this didn't exist, you still have this term to give you noise. So therefore, it doesn't matter how strong your signal is with respect to the noise, it will still be washed out by the interference. So in other words, your probability of error curves, you're accustomed to probability of error curves that look like this, that just sort of go down and down and down and down. What you would have in this case is something like this. So if you were plotting this with respect to, actually if you're plotting it with respect to N0, this is what it looks like. And then when you would get the CDMA, something like that. So there sort of comes a point at which it doesn't really become valuable to try to decrease N0.